Imagine a world not our own, yet under the very same sun. A world where the ground trembled beneath the footsteps of giants. Herds of woolly mammoths, their tusks curving towards the sky, roamed vast, frozen steppes. Saber-toothed cats, with fangs like daggers, hunted in the shadows of immense forests. Giant sloths, taller than elephants, ambled through ancient landscapes. For millions of years, these megafauna were the undisputed kings of the earth, shaping ecosystems by their very existence. They survived ice ages, volcanic eruptions, and dramatic shifts in the planet's climate. And then, in the geological blink of an eye, they vanished. What force of nature, or what new arrival on the world stage, could silence the thunder of these titans? The answer is a story of survival, adaptation, and a profound change that forever altered the face of our planet. This is the story of the end of an era. Imagine a world not our own, yet still our Earth. A world breathing under the weight of giants. This was the late Pleistocene, an epoch that ended a mere 12,000 years ago. It was a time when the pulse of the planet was felt in the thunderous footsteps of colossal beasts. Across every continent, save for Antarctica, life reached a scale that dwarfs our modern imagination. This was the age of the megafauna, a term for animals with a body mass exceeding 100 pounds. But many were far, far larger. In North America, giant ground sloths, some as tall as a giraffe when standing on their hind legs, ambled through woodlands, their massive claws stripping leaves from high branches. Herds of imperial mammoths, standing over 13 feet at the shoulder, roamed from the grasslands of Mexico to the Canadian tundra. In South America, the glyptodont, an armored mammal the size of a small car, grazed peacefully, its fused, dome-like shell a fortress against predators. Australia, a continent of unique evolutionary experiments, was home to the diprotodon, a rhinoceros-sized wombat, the largest marsupial that ever lived. And across the vast cold plains of Eurasia, the woolly rhinoceros, its body covered in a thick shaggy coat, used its massive horn to sweep away snow in search of frozen vegetation. These titans were not mere curiosities, they were the architects of their ecosystems. They were ecosystem engineers, whose grazing patterns maintained vast grasslands, whose migrations dispersed seeds over immense distances, and whose very presence shaped the landscape. Their immense bodies supported a complex web of life, from the predators that hunted them to the insects that lived on their hides. For hundreds of thousands of years, this world of giants thrived, adapting to the rhythmic cycles of glacial advance and retreat. They were the undisputed masters of the planet, a testament to life's ability to achieve magnificent size and diversity. But this vibrant, thrumming world, seemingly so permanent and powerful, was on the precipice of an unprecedented collapse. An invisible clock was ticking down, and a wave of extinction was gathering on the horizon, ready to sweep this majestic kingdom away forever. The question is not just what happened, but why? What force could possibly erase a world of giants? At the close of the last great ice age, something strange happened. As the colossal ice sheets that had covered much of the northern hemisphere began their final, steady retreat, the world grew warmer. Forests expanded, grasslands flourished, and new habitats opened up. Logically, this should have been a time of prosperity for the planet's inhabitants, especially the large, cold-adapted animals. Instead, it heralded their doom. This is the Pleistocene Paradox. Why did the world's megafauna, which had successfully weathered numerous previous ice ages and warming periods, suddenly vanish during this particular transition? The extinction event was swift and devastatingly selective. It wasn't a random die-off, it specifically targeted the largest of the large. Over half of the world's megafauna species disappeared. For decades, two primary culprits have stood at the center of the investigation: climate and humans. The climate change hypothesis argues that the warming at the end of the Pleistocene was uniquely rapid and disruptive. As glaciers melted, sea levels rose, and weather patterns shifted dramatically. The vast, cool, dry grasslands, like the mammoth steppe that stretched across Eurasia and North America, were replaced by denser, wetter forests and bogs. This fundamental change in vegetation could have starved the giant grazers, who were adapted to a diet of grasses and sedges. The ripple effect would have been catastrophic, leading to the collapse of the entire food web, including the apex predators who depended on them. Yet, a glaring question undermines this theory. These animals and their ancestors had survived at least 20 previous glacial-interglacial cycles, many with similarly dramatic climate shifts. Why was this time different? What new element was present on the landscape that had never been there before? This leads to the second, more controversial suspect. The timing of the extinctions aligns with uncanny precision to the arrival and proliferation of a new and uniquely resourceful predator on each continent: Homo sapiens. Modern humans, armed with sophisticated tools, cooperative hunting strategies, and the power of abstract thought, were spreading out of Africa and across the globe. Could this clever, adaptable primate have been the decisive factor? The debate rages on, a scientific mystery pitting the immense forces of nature against the growing power of human ingenuity. Of all the lost giants of the Ice Age, one reigns supreme in our collective imagination: the woolly mammoth. It is the icon of the Pleistocene, a symbol of power, resilience, and adaptation to a harsh, frozen world. To understand the end of the megafauna, we must first understand their most famous representative. Mammothus primigenius, the woolly mammoth, was a masterpiece of evolutionary engineering. Standing up to 11 feet tall and weighing over 6 tons, it was perfectly equipped for life on the frigid mammoth steppe. Its most distinctive feature was its coat, a double layer of long, coarse guard hairs covering a dense, woolly undercoat, providing superb insulation against biting winds and sub-zero temperatures. Beneath the skin, a thick layer of fat, up to 4 inches deep, offered further protection and served as a crucial energy reserve during the long, lean winters. Even its anatomy was fine-tuned for the cold. Its ears were small, much smaller than those of modern elephants, minimizing heat loss. Its blood contained a special type of hemoglobin that released oxygen at very low temperatures, ensuring its extremities did not freeze. The mammoth's magnificent tusks, which could grow up to 16 feet long in large males, were not just for show. They were versatile tools, used in battles with rivals for mates, as a defense against predators, and, most importantly, to sweep aside snow and break through ice to uncover the buried grasses and shrubs that formed the bulk of their diet. Like modern elephants, they were highly social creatures. Fossil trackways and bone beds suggest they lived in herds led by an experienced matriarch who guided her family along ancient migration routes, passing down vital knowledge of where to find food and water through the changing seasons. Our intimate knowledge of these animals comes from the remarkable state of preservation of remains found frozen in the Siberian permafrost. Incredibly complete specimens, like the baby mammoth named Lyuba, discovered in 2007, have allowed scientists to study their muscles, internal organs, and even their last meals. They were, by every measure, a supremely successful species, dominating the northern hemisphere for hundreds of thousands of years. They were the undisputed kings of the cold. And yet, they vanished. If this perfectly adapted titan could not survive the changes at the end of the Ice Age, what chance did anyone else have? The world of giants was also a world of giant hunters. For every massive herbivore that roamed the Pleistocene landscapes, there was a predator exquisitely adapted to the challenge of hunting it. This was an age of carnivores, on a scale we can barely comprehend today, a time when the balance of nature was maintained by tooth and claw in a constant, high-stakes evolutionary arms race. In the Americas, the undisputed celebrity was Smilodon fatalis, the saber-toothed cat. It was not a tiger, but a unique and powerful feline, built more like a bear with a muscular neck and powerful forelimbs. Its most famous features, the 7-inch canine teeth, were not for crushing bone, but for delivering a precise, shearing bite to the soft throat or belly of its prey after an ambush. It was a specialist in taking down large, slow-moving animals like bison and young mammoths. Competing with it was the formidable American lion, Panthera atrox. 25% larger than any lion today, it was a fearsome hunter, likely operating in prides to bring down formidable prey like horses and camels on the open plains. But perhaps the most intimidating predator of all was the giant short-faced bear, Arctodus simus. Standing nearly 6 feet tall at the shoulder on all fours and over 12 feet when reared up, it was one of the largest terrestrial mammalian carnivores ever to exist. Its long, slender legs suggest it was not an ambush hunter, but a pursuer, capable of running down prey over long distances. Or perhaps it was the ultimate intimidator, using its immense size to chase smaller predators away from their hard-won prizes. Alongside these titans were packs of dire wolves, Enotion dirus, heavier and more robust than modern gray wolves, who specialized in hunting the Ice Age horses and bison that populated the continent. These apex predators were the capstone of the Pleistocene ecosystem. They kept herbivore populations in check, weeding out the weak and the old, ensuring the health of the herds and the grasslands they depended on. Their existence was a testament to the richness and vitality of their world, but their very specialization was their greatest vulnerability. Their fates were inextricably tied to the fate of the giants they hunted. When the great herds began to falter, the reign of the great hunters was destined to end as well. Roughly 3 million years ago, a monumental geological event reshaped the destiny of life in the Western Hemisphere. After tens of millions of years of separation, the continents of North and South America were finally joined by the formation of the Isthmus of Panama. This narrow strip of land became a two-way bridge, triggering one of the greatest natural experiments in the history of life on Earth, the Great American Interchange. Before this connection, South America was an island continent, much like Australia today. It had its own unique and ancient lineage of animals, dominated by marsupials, strange hoofed creatures called ungulates, and giant, flightless terror birds. North America, connected to Eurasia via the Bering Land Bridge, was home to more modern placental mammals, including the ancestors of horses, camels, elephants, and advanced carnivores. When the gateway opened, a massive wave of migration began in both directions. From the north, waves of highly competitive placental mammals surged southward. Gomphotheres, relatives of mammoths, saber-toothed cats, bears, deer, and horses all established themselves in the new continent, transforming its ecosystems. From the south, a smaller but equally fascinating group of animals ventured north. Giant ground sloths, some weighing several tons, lumbered into North America. Glyptodonts, the heavily armored relatives of armadillos, followed. Porcupines and armadillos also made the journey, and their descendants survive in the north to this day. This grand mingling of fauna created an unprecedented level of biodiversity, especially in South America, which for a time hosted a bizarre and wonderful mix of native and immigrant species. However, the interchange was not an equal exchange. The northern invaders, having evolved in a more competitive environment with a greater diversity of predators, generally outcompeted their southern counterparts. Many of South America's unique native species were driven to extinction. This colossal biological event set the stage for the final chapter of the megafauna. It created the specific, complex mix of giant animals that the first humans would encounter when they finally arrived in the Americas. The interchange built a rich, intricate, but perhaps ultimately fragile ecosystem. The complex web of life it wove over millions of years was about to face its greatest test, a new pressure that would push it past its breaking point. Long before it was the land of kangaroos and koalas, Australia was a different world entirely. It was a continent of giants, a lost kingdom of marsupial megafauna that seems almost mythical to the modern mind. For millions of years, this isolated landmass was an evolutionary laboratory, producing a cast of creatures unlike any seen elsewhere on Earth. Imagine a wombat the size of a rhinoceros, the mighty Diprotodon, weighing nearly 3 tons, peacefully browsing in eucalyptus forests. Picture Procoptodon, a giant short-faced kangaroo standing 10 feet tall, with a single massive toe on each foot, capable of covering huge distances. The predators were just as formidable. Lurking in the scrub was Megalania, a goanna lizard growing up to 20 feet long, a true land dragon armed with a venomous bite. And in the trees and caves, the Thylacoleo carnifex, the marsupial lion, waited. Not a cat, but a powerful predator with immense bolt-cutter-like teeth, it was arguably the most specialized mammalian carnivore of its time. These titans had dominated their environment for eons, weathering countless ice ages and climate shifts. Their reign seemed unassailable. But then, something changed. Around 46,000 years ago, in a geological instant, they vanished. Over 90% of Australia's large animal species disappeared forever. For decades, scientists have debated the cause of this catastrophic loss. One theory points to climate. Australia was becoming increasingly arid, and perhaps the fragile ecosystems that supported these giants simply collapsed. Yet, these animals had survived previous droughts. The other theory points to a new arrival. The first humans reached Australia at least 65,000 years ago, living alongside the megafauna for nearly 20 millennia. These were not primitive scavengers, but intelligent, adaptable people. Evidence of their presence is widespread, particularly in the form of charcoal deposits in ancient sediment layers. Some researchers believe they initiated a practice of systematic landscape burning, altering the environment to promote grasslands and hunt more effectively. This fire stick farming could have radically reshaped the continent's flora, destroying the habitats the megafauna relied upon. Direct evidence of hunting is scarce, but the timing is deeply suggestive. The giants that had endured millennia of natural change disappeared within a few thousand years of encountering this new, clever primate. Was it a perfect storm of climate stress and human pressure? Or was the arrival of humanity the final, decisive blow that silenced the thunder of Australia's lost monsters forever? The questions that haunt the red soil of Australia would soon echo across the entire planet. To understand the force that would challenge the megafauna, we must travel back in time and space to Africa's Great Rift Valley, millions of years before the Australian extinctions. This is the cradle of humanity, the stage upon which our own story began. Here, a profound environmental transformation was underway. The dense tropical forests were retreating, giving way to vast, open savannas. For our arboreal ancestors, the world was changing, and they had to change with it. Forced from the relative safety of the trees, early hominins like Australopithecus afarensis, famously represented by the fossil Lucy, took a monumental step. They rose up and walked on 2 legs. This adaptation, bipedalism, was a gamble. It made them slower and more exposed than 4-legged animals. But it offered incredible advantages. It freed the hands to carry food, to hold infants, and eventually to create tools. It allowed them to see over the tall grasses, to spot predators and opportunities alike. For millions of years, these early ancestors were a minor part of the ecosystem. They were not the mighty hunters, but the hunted. They lived in the shadow of true apex predators, saber-toothed cats, giant hyenas, and powerful crocodiles. Their first tools, the simple Oldowan choppers of Homo habilis, the handyman, were instruments of opportunism, used for smashing bones to get at marrow, or cutting meat from carcasses left by more powerful killers. They were intelligent, social, and resourceful, but they were still fundamentally prey. Survival depended not on individual strength, but on the strength of the group. Cooperation, communication, and a growing awareness of their environment were their primary assets. They learned the movements of the great herds, the habits of the carnivores, and the secrets of the seasons. They formed tight-knit bands, sharing knowledge and protecting one another in a world filled with danger. They were a new kind of ape, one with a burgeoning intellect and a capacity for collaboration that set them apart. Yet, for all their cleverness, their impact on the planet's megafauna was negligible. They were just another primate, carving out a niche on the African plains. What, then, propelled this vulnerable creature from the periphery of the food chain to its absolute center? What was the catalyst that would transform a marginal scavenger into the world's most effective predator? The answer was not in their bones or their muscles, but in the ideas they were about to grasp, ideas that would manifest as two of the most powerful forces ever wielded by life on Earth. For every creature on the ancient savanna, a wildfire was a terrifying force of pure destruction, a signal to flee. But for one lineage of hominins, this elemental power would become something else entirely, a tool, a weapon, and a companion. The controlled use of fire represents one of the most significant turning points in the human story. While the exact timeline is debated, evidence suggests our ancestor, Homo erectus, began harnessing flame perhaps 1 million years ago. This discovery remade their world. The campfire became a fortress of light and warmth in the deep, dangerous night, keeping formidable predators at bay. It transformed their diet. Cooking meat and tubers not only neutralized pathogens, but also unlocked a wealth of calories and nutrients that were previously indigestible. This surge of high-quality energy is believed to have been a crucial factor in the dramatic expansion of the hominin brain. The hearth became the heart of the community, a place for sharing food, for social bonding, and for the development of complex communication. As our ancestors mastered fire, they were also perfecting their relationship with stone. The simple choppers of the past gave way to a tool of remarkable ingenuity and design, the Acheulean hand axe. Symmetrical, teardrop-shaped, and remarkably consistent in its form for over 1 million years, the hand axe was the world's first designed object. It required foresight, planning, and a sophisticated understanding of fracture mechanics to create. It was a multi-tool, used for butchering carcasses, scraping hides, digging for roots, and shaping wood. Holding one is to hold a thought from a mind that existed 1 million years in the past. Armed with these twin technologies, our ancestors were no longer just scavengers. They were becoming strategic hunters. Fire could be used to drive herds of large animals towards cliffs or into ambushes. The hand axe and sharpened wooden spears allowed them to process their gains with new efficiency. This was a cognitive leap. They were not just reacting to their environment, they were actively shaping it to their will. They could now defend themselves more effectively, nourish their growing brains more completely, and organize their social lives with greater complexity. They were no longer simply another African ape. They were becoming something new, a creature that carried its own environment with it, a bubble of warmth and safety in the form of the campfire, and an extension of its will in the form of the crafted stone. The world had become a place of immense possibility, and now, equipped with flame and stone, They were ready to leave their African cradle and explore it. Around 70,000 years ago, a small group of anatomically modern humans, Homo sapiens, stood at a threshold. Perhaps on the shores of the Red Sea, they looked across the water towards the vast, unknown continent of Asia. They were about to embark on the greatest journey of exploration in the history of life, a planetary expansion that would change the world forever. This was the pivotal out of Africa migration. Following coastlines, these bands of hunter-gatherers moved with remarkable speed. Within just a few thousand years, they had spread across southern Asia. By 65,000 years ago, their descendants had made the sea crossing to Australia, and by 45,000 years ago, they were pushing into the cold, challenging landscapes of Europe. The world they entered was a true planet of the giants. Europe was home to herds of woolly mammoths, woolly rhinos, and the formidable cave bear. Asia teemed with giant deer and ancient elephants called stegodon. These ancient ecosystems had been stable for millennia, ruled by a balance between massive herbivores and powerful predators. But the new arrivals were a predator unlike any other. What gave these humans their decisive edge? It was not physical strength. They were less robust than the Neanderthals they encountered in Europe. Their advantage was in their minds. They were products of the cognitive revolution, possessing a new capacity for abstract thought, sophisticated planning, and fully symbolic language. This allowed them to communicate complex ideas, to form larger and more cohesive social networks, and to innovate technologically at an unprecedented rate. Their toolkit was far more advanced than that of earlier hominins. They created specialized blades, bone needles for sewing tailored clothing, and most critically, deadly projectile weapons. The spear thrower, or atlatl, was a force multiplier, allowing a hunter to launch a spear with incredible velocity and accuracy from a safe distance. It was a revolution in hunting technology. As these modern humans swept across the globe, a disturbing pattern emerged. From Europe to Asia to Australia, the timeline of their arrival often coincided with a dramatic decline in large animal populations. The great beasts that had survived countless ice ages began to disappear. Was it the sole fault of these new hunters? Or did their arrival coincide with periods of intense climate stress, creating a lethal combination of pressures? The debate continues, but the correlation is undeniable. For thousands of years, one corner of the world remained a separate, isolated paradise for megafauna, the Americas. Guarded by vast continental ice sheets, this new world was the last great preserve of Pleistocene giants. But the ice was beginning to melt, and a path was opening. The most skilled hunters the world had ever known were about to enter a continent that had never known their kind. At the end of the last ice age, the Americas were a world lost in time. It was a continent of spectacular beasts, Columbian mammoths towering over the plains, giant ground sloths browsing on trees, and saber-toothed cats stalking formidable prey. This megafaunal paradise had existed for millennia, evolving in isolation, with its animals having no instinctual fear of a bipedal primate. But around 13,500 years ago, that changed with the appearance of a new people and their revolutionary technology. We call them the Clovis culture, named after a site in New Mexico where their distinctive artifacts were first found. Their calling card, their signature left across an entire continent, is the Clovis Point. This was no crude spearhead. It was the pinnacle of Stone Age ballistic engineering. Beautifully crafted from high-quality stone like flint or chert, it was large, leaf-shaped, and razor-sharp. Its most ingenious feature was the central groove, or flute, carved from its base. This channel allowed the point to be hafted securely onto a wooden shaft, creating a durable and devastatingly effective weapon when launched from a spear thrower. Finding a Clovis point is to find the fingerprint of these ancient hunters. And crucially, these points are frequently discovered among the bones of mammoths and other extinct megafauna. At sites like the one in Naco, Arizona, multiple points have been found within a single mammoth skeleton. This is the clearest evidence we have of the interaction between the first Americans and the giants they shared the land with. The hunt itself would have been a masterpiece of strategy and courage. A coordinated group of hunters, using their knowledge of the landscape and animal behavior, would isolate an individual from the herd. Using the leverage of the atlatl, they could deliver powerful, penetrating strikes from a distance, targeting vital areas. It was this efficiency that led to the controversial overkill hypothesis. This theory proposes that the Clovis hunters were so effective and the American megafauna so naive to the new threat that these human bands swept down through the continents in a wave of extinction, wiping out dozens of species in just a few centuries. More likely, the truth is a combination of factors. The end of the Ice Age brought rapid, severe climate shifts, stressing animal populations and altering their habitats. The Clovis hunters arrived in this world of instability, delivering a final, decisive blow to species already on the brink. The evidence is in the timeline. The Clovis culture flourished for only a few hundred years. Then, just as suddenly as they appeared, their signature points vanished from the archaeological record. At the very same time, their giant prey disappeared forever. The hunt was over. The world they were equipped to master was gone, leaving a quieter, emptier continent in its wake. In the mid-20th century, a bold and unsettling idea began to take hold in the scientific community, one that placed humanity at the center of a prehistoric catastrophe. This was the overkill hypothesis, championed most famously by geoscientist Paul S. Martin. The theory presents a dramatic and compelling narrative. As the first modern humans, known as the Clovis people, crossed the Bering Land Bridge and spread into the Americas around 13,000 years ago, they entered a world teeming with giant animals that had never before encountered such a sophisticated predator. These megafauna, from the colossal woolly mammoth to the formidable saber-toothed cat, were naive to the danger posed by these small, tool-wielding newcomers. According to Martin's Blitzkrieg model, these highly skilled hunters advanced rapidly across the continent, their arrival marked by a wave of extinctions. The evidence seemed persuasive. The timing was uncanny. The disappearance of dozens of large mammal species occurred in a geological blink of an eye, right after the first archaeological evidence of a widespread human presence. The primary piece of evidence was the Clovis Point itself, a masterfully crafted stone spearhead found at kill sites directly associated with mammoth remains. These artifacts were the smoking gun, seemingly linking human hunters directly to the demise of the giants. Proponents of this theory argue that even a small population of efficient hunters, focusing on large, slow-reproducing animals, could have had a devastating impact, triggering a cascade of extinctions that reshaped the entire ecosystem. However, the overkill hypothesis is not without its critics. They ask pointed questions. If human hunters were so ruthlessly effective, why is there a relative scarcity of kill sites across such a vast continent? The archaeological record shows evidence of mammoth hunting, but is it enough to account for the complete eradication of an entire class of animals? Furthermore, why did some large species, like the bison, survive the onslaught while others vanished? These lingering questions cast a shadow of doubt on the idea of a purely human-driven extinction. The theory forces us to confront a disturbing possibility, that one of humanity's first major acts upon entering a new world was to systematically eliminate its most magnificent inhabitants, leaving a trail of bones in its wake. Just as the Earth was beginning to thaw from the grip of the last great ice age, something went terribly wrong. For thousands of years, the planet had been on a steady warming trend. The colossal ice sheets that covered much of the northern hemisphere were in retreat, and life was adapting to a warmer, wetter world. Then, with shocking abruptness, the warming stopped and reversed. the planet was plunged back into a deep freeze. This dramatic period, which began around 12,900 years ago, is known as the Younger Dryas. It was a climatic cold shock that lasted for over a millennium, a sudden and brutal return to near-glacial conditions. The leading theory for this planetary whiplash centers on the heart of North America. As the massive Laurentide ice sheet melted, it created an immense body of fresh water known as Lake Agassiz, larger than all of the modern Great Lakes combined. Scientists believe that the ice dam holding this lake in place catastrophically failed. An unimaginable volume of frigid, fresh water surged into the North Atlantic Ocean. This sudden influx is thought to have disrupted the Atlantic meridional overturning circulation, a critical ocean current system that acts like a global heat conveyor, transporting warm tropical waters northward. With this heat pump effectively shut down, temperatures in the northern hemisphere plummeted by as much as 10 degrees Celsius in just a few decades. The consequences were immediate and devastating. Forests that had been advancing northward died off, replaced by barren, wind-swept tundra. Glaciers began to advance once more. For the planet's megafauna, this was a catastrophe. Animals like the mammoth and the mastodon, which had adapted to the specific grasslands and parklands of the late glacial period, saw their habitats vanish from beneath their feet. The sudden environmental stress would have been immense, affecting everything from food availability to reproductive success. The Younger Dryas was a planetary-scale event that fundamentally altered the rules of survival. It raises a critical question. Were the great beasts already on the brink, pushed to the edge by a world that had suddenly turned cold and hostile, long before the first human hunters became a significant threat? While the specter of human hunters provides a compelling villain, another powerful suspect stands accused in the case of the missing megafauna, the climate itself. The argument for climate change as the primary culprit suggests that the end of the Pleistocene was a time of such profound environmental instability that the extinction of the great beasts was all but inevitable. The Younger Dryas was just one episode in a series of wild climatic swings. The planet experienced periods of rapid warming and cooling, a kind of environmental whiplash that repeatedly redrew the map of life on Earth. Ecosystems were in a constant state of flux. Vast, contiguous habitats like the Mammoth Steppe, a unique, cold, dry grassland that stretched across continents, began to break apart. As temperatures rose and precipitation patterns shifted, forests expanded into former grasslands, and grasslands turned into wetlands or arid scrublands. This process, known as habitat fragmentation, was devastating for large, wide-ranging animals. Populations that were once connected became isolated in smaller and smaller pockets of suitable territory. This isolation led to a decrease in genetic diversity, making the animals more susceptible to disease and less able to adapt to further changes. Proponents of the climate-first theory point to several key pieces of evidence. Extinctions occurred in waves that appear to correlate with major climatic shifts, not just with the arrival of humans. In some parts of the world, like Eurasia, megafauna had coexisted with modern humans for tens of thousands of years before they finally disappeared during the major climate upheavals at the end of the Ice Age. If humans were the primary driver, why wait so long? Furthermore, some megafauna species vanished from regions where there is little to no evidence of a human presence at the time of their disappearance. This perspective paints a picture of a world in turmoil, where the fundamental rules of the environment were changing too quickly. The megafauna were specialists, perfectly adapted to the Ice Age world. When that world vanished, their time was simply up. In this view, humans were not the primary cause, but rather witnesses, or at best, minor players, in a much larger drama orchestrated by the planet's own powerful climatic forces. For decades, the debate over the megafauna's disappearance has often been framed as a stark choice between two rival explanations: humanity's spear or nature's cold. In one corner stood the overkill hypothesis, arguing that the arrival of uniquely skilled human hunters was the decisive factor. In the other corner was the climate change hypothesis, asserting that profound environmental instability was the true agent of extinction. Each theory had its compelling evidence and its frustrating inconsistencies. Overkill neatly explained the suspicious timing of extinctions in the New World, but struggled with the scarcity of archaeological proof. Climate change explained the immense environmental stress the animals were under, but couldn't fully account for why the final extinctions happened so rapidly and completely after humans appeared on the scene. But what if this is not an either-or question? A growing consensus among scientists suggests that the truth lies not in choosing one theory over the other, but in combining them. This is the synergistic model, a 1-2 punch theory of extinction. In this scenario, climate change delivered the first body blow. The wild fluctuations at the end of the Pleistocene acted as the great stressor. It weakened megafauna populations, shrank their habitats, reduced their food sources, and pushed them into smaller, more isolated refuges. The giants were already stumbling, their numbers dwindling, their resilience worn thin by a world in constant flux. Then, onto this chaotic stage stepped a new and unpredictable force: Homo sapiens. These weren't just another predator. They were intelligent, cooperative, and armed with innovative technology. They encountered animal populations that were already vulnerable and ecologically stressed. Hunting pressure that might have been sustainable for a healthy, continent-spanning population proved to be the final, decisive blow for the struggling survivors. An elegant analogy holds that climate change loaded the weapon, while human hunters pulled the trigger. This combined theory helps resolve many of the old paradoxes. It explains why megafauna in Africa, which had co-evolved with humans for millennia and developed behavioral adaptations, fared so much better. It also explains the terrifying speed of the extinctions in the Americas and Australia, where naive and already stressed animals met a new super-predator for the first time. The question is no longer simply humans or climate. The real mystery is understanding the precise interplay between these two powerful forces and how their convergence created a perfect storm of extinction. To untangle the complex story of the megafauna's end, scientists are no longer limited to simply studying bones and stone tools. A revolution in analytical techniques is allowing us to read the deep past with unprecedented detail, revealing clues hidden within the very molecules of the lost world. One of the most powerful new tools is the study of ancient DNA. By carefully extracting and sequencing genetic material from fossilized remains, researchers can reconstruct the genetic history of an extinct species. This allows them to track population sizes and genetic diversity over thousands of years. In several key studies, ancient DNA has revealed that megafauna populations, such as the woolly mammoth, were already in a steep decline and losing genetic diversity long before humans became widespread, providing strong evidence for significant climate-induced stress. Another innovative technique is stable isotope analysis. The chemical composition of an animal's bones and teeth acts as a permanent record of its diet and the environment it lived in. By analyzing the ratios of different isotopes of elements like carbon and nitrogen, scientists can determine if an animal was undergoing dietary stress or being forced to change its feeding habits as its preferred vegetation disappeared. Perhaps the most ingenious method involves counting the spores of a fungus called Sporormiella. This fungus grows exclusively on the dung of large herbivores. By drilling cores from lakebed sediments and counting the concentration of these spores at different layers, scientists can create a detailed timeline of megafauna population density. In many regions, these spore counts show a dramatic crash in large animal populations that aligns perfectly with periods of major climate change, sometimes preceding the first evidence of heavy human hunting. When combined with traditional methods like pollen analysis, which reveals how plant communities changed over time, these techniques create a high-resolution picture of the past. We can now see the sequence of events, the climate shifts, the vegetation changes, the animal populations crash, and then, finally, human artifacts become common. This new, multi-proxy evidence is painting a much more nuanced picture. It strongly suggests that the megafauna were caught in a deadly convergence of forces. The story of their demise is written not just in stone, but in the soil, the spores, and the very DNA they left behind. Our challenge is simply to become better readers of this ancient, tragic text. To truly understand the world in which the megafauna vanished, we must look beyond the bones and spear points. We must turn to the planet's own memory, archived in the most unlikely of places, ancient ice and microscopic dust. In the heart of Greenland and Antarctica, scientists drill deep into glaciers, extracting cylinders of ice that are veritable time capsules. Each layer represents a season's snowfall, and trapped within these layers are tiny bubbles of Earth's ancient atmosphere. By analyzing the carbon dioxide and methane in these bubbles, researchers can reconstruct past temperatures with astonishing precision. What these ice cores reveal is not a story of gradual, gentle change, but one of violent climatic shifts. The end of the Pleistocene was a turbulent era, culminating in a dramatic and sudden cold snap known as the Younger Dryas, which began around 12,900 years ago. In a matter of decades, average temperatures in the northern hemisphere plummeted, plunging the warming world back into near-glacial conditions. The ice tells us what happened to the climate, but to see what happened to the landscape, we must look elsewhere. In the silent depths of lakes and bogs, another record was being kept, grain by grain. This is the world of palynology, the study of ancient pollen. Every spring, for millennia, trees and plants released vast clouds of pollen, each grain uniquely shaped according to its species. A tiny fraction of this pollen settled in lake beds, where it was preserved in layers of sediment. By drilling cores into these ancient lakes, scientists can read the history of the surrounding vegetation. The story told by the pollen is as dramatic as that of the ice. Across North America and Eurasia, the pollen layers corresponding to the Younger Dryas show a catastrophic transformation. The evidence of lush spruce and pine forests, the preferred habitat for browsing mastodons and mammoths, abruptly vanishes. It is replaced almost overnight by the pollen of tundra grasses and hardy, cold-resistant shrubs like dwarf birch. The world's ecosystems were completely remade. The megafauna's environment, the foundation of their existence, was pulled out from under them. Their food sources disappeared, their forests became frozen plains, and their migratory routes were altered by expanding ice sheets. This powerful climatic evidence presents a compelling case. It suggests the giants were victims of a planetary catastrophe, a climate shift so rapid and severe that adaptation was impossible. The question is no longer if the climate changed, but if this environmental collapse was the sole killer, or if it merely weakened the herds, leaving them exposed and vulnerable to a new and rising pressure that was stalking the changing landscape. The Great Extinction event was not a single, instantaneous planetary purge. It was a staggered, drawn-out process, a slow fading that played out over thousands of years and across vast geographies. While the mammoths and mastodons vanished from the great continents of North America and Eurasia around 10,000 years ago, some populations found temporary sanctuary, making a final, poignant stand in isolated corners of the globe. The most famous of these refugees is Wrangel Island, a remote outpost in the Arctic Ocean. Here, cut off from the mainland by rising sea levels, a population of woolly mammoths survived. They were smaller than their continental ancestors, a phenomenon known as insular dwarfism, but they were survivors. For 6,000 years after the last mammoths disappeared from Siberia, this isolated herd endured. They were contemporaries of the ancient Egyptians, still roaming the Arctic tundra as the Great Pyramids were being built. Islands, by their very nature, offered protection. They were often free from the initial waves of human hunters and could act as buffers against the most extreme climatic shifts affecting the continents. Similar stories unfolded elsewhere. Dwarf elephants and hippos survived on Mediterranean islands like Crete and Cyprus long after their mainland relatives were gone. Giant ground sloths, thought to be extinct, found a temporary haven on islands off the coast of Central America. These island populations represent the final embers of the Pleistocene fire. But their isolation, once a strength, ultimately became a fatal weakness. Small populations inevitably lead to a loss of genetic diversity, making the animals highly susceptible to disease or a sudden environmental downturn. And eventually, the forces that had remade the continents caught up with them. The climate continued to change, altering their fragile island habitats. And finally, humans arrived. Archaeological evidence on Wrangel Island suggests that the first humans appeared around the same time the last mammoths disappeared, about 4,000 years ago. Whether they hunted the last few individuals or simply competed for scarce resources, their arrival appears to have sealed the mammoth's fate. These last stands were not confined to islands. In deep, protected valleys in the Rocky Mountains or specific river basins in Siberia, small pockets of megafauna may have held on for a few extra centuries. These were oases of stability in a world of chaos. But one by one, these final holdouts were extinguished. The story of the last giants is a testament to their incredible resilience, but also to the seeming inevitability of their decline. Their slow, staggered disappearance shows us that extinction is a process, not just an event, and it begs a new question. What became of the world they left behind? When the last mammoth fell, the silence that followed was more than just the absence of its footsteps. It was the sound of an entire ecosystem beginning to unravel. The megafauna were not merely inhabitants of the Pleistocene world, they were its architects, its engineers. Their removal was like pulling the keystone from an arch, causing a cascade of consequences that fundamentally reshaped the planet's landscapes. We think of mammoths and mastodons as grazers, but they were also gardeners on a continental scale. Pushing through forests, they toppled trees, creating clearings and meadowlands that allowed a greater diversity of plants to thrive. They were also master seed dispersers. By consuming vast quantities of fruit and depositing the seeds miles away in their dung, they maintained the health and range of countless plant species. With their disappearance, this dynamic process ceased. Forests, no longer managed by these giant herbivores, became darker, denser, and more uniform, a process scientists call massification. The very nature of the biome changed. The most dramatic example of this was the vanishing of the mammoth steppe. This was a unique, lost ecosystem that once stretched from Western Europe across Asia and into North America. It was not a barren tundra, but a highly productive, cold, dry grassland, capable of supporting an incredible diversity and density of animal life. This rich environment was maintained by the constant activity of massive herds. Their grazing prevented shrubs from taking over, their trampling aerated the soil, and their waste fertilized the plains. When the great grazers vanished, the mammoth steppe vanished with them. The unmanaged grasses grew long, died, and created a thick thatch that insulated the ground, preventing deep seasonal thaws. The productive grasslands were replaced by soggy, unproductive mosses, scrublands, and coniferous forests. The collapse rippled up the food chain. Predators like the saber-toothed cat, the American lion, and the giant short-faced bear, which had evolved to hunt massive prey, were left without a food source. They starved into extinction. Scavengers, from dire wolves to the colossal terror-torn birds, lost the steady supply of giant carcasses that had sustained them. Even the frequency of fire was altered. Without the mega herbivores consuming tons of biomass, dead plant matter accumulated. Sediment cores from the period show a dramatic spike in charcoal deposits, indicating a shift to a world of more frequent and intense wildfires. The world we inherited is an echo of what it once was. The landscapes we consider natural are, in many ways, impoverished, haunted by the absence of the giants who built them. Their extinction was not just the loss of species, it was the loss of an entire operating system for the planet. The great beasts of the Pleistocene may be gone, but they are not entirely forgotten. They have left behind ghostly echoes of their existence, not in fossils or cave paintings, but in the DNA of the living plants and animals that surround us today. To find this evidence, one only needs to ask a simple question. Why does an avocado have a seed so large that no native animal in the Americas can swallow it? The answer is a concept known as an evolutionary anachronism. The avocado tree co-evolved with a creature that could eat its fruit whole and disperse its enormous seed, the gomphothere there, a giant, four-tusked relative of the elephant. The gomphothere there is long extinct, but the avocado tree still produces fruit as if its giant gardening partner will return tomorrow. It is carrying a genetic memory of a lost world. This phenomenon is surprisingly common. The Osage orange tree produces a large, lumpy, inedible fruit that simply falls and rots, its dispersal agent, perhaps a mastodon or giant ground sloth, long gone. The honey locust tree arms its trunk with formidable, spear-like thorns, far too large and menacing to deter a modern deer or rabbit. These thorns were an effective defense against the immense browsing power of a mastodon. These plants are haunted, equipped with traits for a world that no longer exists. The ghosts are present in the animal kingdom as well. Consider the pronghorn of the North American plains. It is the fastest land animal in the Western Hemisphere, capable of sustained speeds that far exceed those of its only major modern predator, the coyote. Why this incredible, seemingly excessive speed? The pronghorn is still running from a ghost predator, the extinct American cheetah, a long-legged cat that was more than a match for the pronghorn's swiftness. The pronghorn's genes still carry the imperative to escape a pursuer that vanished 10,000 years ago. These genetic ghosts offer a profound insight into the intricate web of relationships that defined the Pleistocene. They reveal how deeply the megafauna were integrated into their ecosystems. Understanding these connections has even inspired radical new ideas in conservation, such as rewilding, the concept of introducing modern ecological proxies, like elephants or wild horses, to try and restore these lost functions. The world around us is a living museum, filled with relics of a grander age. In the fruit we eat, the trees we see, and the animals that run across our plains, the giants of the Ice Age have left their indelible signature. For millions of years, the earth trembled under the footsteps of giants. Then, in a geological moment, they fell silent. We have followed their trail through time, examining the clues left in fractured bones, in layers of ancient pollen, and in the very DNA of the world they left behind. The debate over their demise has centered on two powerful forces: a rapidly changing climate and the arrival of a new, uniquely resourceful predator. The verdict of modern science is that it was not one or the other, but a devastating combination of both. The end of the Ice Age was a period of extreme climatic volatility. The Younger Dryas event subjected the megafauna to immense stress, shrinking their habitats, altering their food supply, and fragmenting their populations. They were weakened, disoriented, and living on the edge. Into this chaotic world stepped Homo sapiens. Armed with sophisticated projectile weapons, cooperative hunting strategies, and the intelligence to adapt to any environment. Our ancestors were a pressure the likes of which the world had never seen. For herds already struggling to survive in a changing world, this new, persistent threat was the final, decisive blow. It was a perfect storm of natural change and human ingenuity. In many ways, the disappearance of the megafauna can be seen as the first great extinction of the Anthropocene, the age of humans. It was the first time our species profoundly and permanently altered the biodiversity of the entire planet. It set a precedent, marking the beginning of our role as the world's dominant agent of ecological change. The parallels to our current situation are impossible to ignore. Today, the world's remaining large animals, the elephants, rhinos, tigers, and whales, are facing the same two-front war. They are besieged by a rapidly changing climate and by relentless human pressures, from habitat loss to direct exploitation. The story of the mammoth and the mastodon is not just a fascinating tale of the distant past. It is a profound and urgent cautionary tale for the present. It teaches us about the fragility of even the most magnificent creatures, the cascading consequences of extinction, and the immense power our species wields. We live on a planet shaped by the absence of the megafauna, an absence that has impoverished our world in ways we are only now beginning to comprehend. The question is no longer who to blame for their disappearance, but whether we will learn from their story. The ghosts of the Ice Age have a final, critical lesson to teach us, if only we will listen before the last of today's giants fall silent forever.